Hi everyone, welcome back. We're going to be talking about unions and intersections of sets in this video. So here I have two sets, A and B, and I have this diagram here. And we notice that these two regions representing A and B have some intersection, right? Just visually. And we want to give some mathematical idea behind what the union and intersection of these sets would be. So we can kind of visually fill in what regions correspond to the intersection union. So I'll use red if it lets me. Okay, cool. I'll use red for the intersection. We can see that this region here would constitute the intersection between A and B. So the notation we use is A, and then this big upside down U, B. So read this as A intersect B, or the intersection of A and B. And that constitutes of the set of elements that are shared by A and B. So if I have some element here that I call X, then X is in A, but also X is in B. Right? So say X in A intersect B implies X in A and X in B. Okay. Then I could consider the union of these two sets. And what the union means is that we're considering these two sets taken entirely together. So we're looking at all the elements of A together with all the elements of B and what total set that forms. So I could just fill that in here. So we're going to look at all of A, including the intersection, and then all of B. The last time I recorded this, I made a joke about Abraham Lincoln and the Civil War. I don't think I can bring myself to do it this time. You guys would never known, but I wouldn't be able to live with myself. Okay. So this region, instead of the upside down U, we use a regular U. Then B. So this we have A union B, or the union of A and B. And so now if we think about what does it mean for X to be in the union of A and B? Well, if we look at our diagram, we see that X can be in A, right? So in this region. But it doesn't have to be, right? It could also be in B, in this whole region. Where X cannot be is outside of both of these, right? So we can't have X be here. That's not part of the union of A and B. So what we're saying then is that we could have X in A, or we could have X in B. And this is consistent with our inclusive OR that we defined previously with logical propositions, because it's okay for X to be in the intersection of A and B. Right? So if X is in A and X is in B, it also satisfies this statement, which means that X would be in the union of A and B. So what we could say then is that X in the intersection of A and B would imply that X is in the union of A and B. And then thinking back to our previous video, we know that this is the same thing as saying that the intersection of A and B, so that whole set, is a subset of the union of A and B. Okay. So this kind of leads us into our definitions for both of these things, where we noted that x is in the intersection of A and B when x is in A and x is in B, right? So equally, we could have this implication going the other direction because really we're just defining the idea of what the intersection is. So we can, is that yellow? No, it's not. Okay. We can give this definition for the intersection that A intersect B is equal to the set of x such that x is in A and x is in B. And remember, we're allowed to use this description of the set as sort of a condition placed on x because of our idea of extensionality. Okay, and correspondingly, we can make a similar definition for the union of A and B. So we have the union of A and B is equal to the set of x such that x is in A or x is in B. Okay. So this is pretty simple. It's simple enough. You guys should be at least somewhat familiar with this. I know, like, at least in the consideration of like probability and probability spaces and stuff like that. Hopefully this is a bit familiar. But the important thing I want to point out is that between last video and this video, we have come up with ideas relating two sets. So something like A is a subset of B, or the intersection of A and B, or the union of A and B. And if you pay close attention, how we've generated these concepts is by taking these, what I guess, I don't think I gave you the term before, but we call logical connectives. So this stuff with implies and or, these things that connect two logical propositions to form another one. If we then make those propositions explicitly x in A and then also x in B, if we take all those together, so we have something like x in A implies x in B, well, that gave us a concept relating two sets. So that in particular gave us A as a subset of B. For and, when we say x in A and x in B, well, that means we're saying that x is in the intersection of A and B. And for or, x in A or x in B means that x is in the union of A and B. So those three concepts are actually pretty natural to construct when you think about just that fact. That really all we're doing is using our natural logical connectives that we came up with, because those really weren't so crazy, and then applying them to the idea of something being an element of a set. Okay, so the next one we're going to talk about this idea of Cartesian products of a set, which sounds maybe mysterious to you right now, but it's actually something that you're secretly familiar with. And then from then on, that lets us talk about the idea of functions between sets. Okay, I'll see you in the next one.